In order to develop a mechanism to trigger the latch in figure 2 and make it a change state, we need to achieve a SR latch that we are showing in this figure 3. Okay, so we have a NOT gate here, another NOT gate here, so which is denoted by N3 and N4, and this output of this NOT gate is given to the input of this NAND gate, and this output of this NOT gate, that is N4, is given to the input of another NAND gate, and with the cross linking concept, the output of one NAND gate is given to the input of another NAND gate. Similarly, the output of another NAND gate is given to the input of other NAND gate. Okay, so like this way, this set reset latch with NAND gate is actually formed. Okay, so now to store actually a specific state, let's say q is equal to logic 1 or q is equal to logic 0 in the latch, we should apply appropriate value to the s and r. Okay, so that is shown in this figure. Now, the state of the input and output is determined accordingly. Now, when the S is at logic 1 or and R is logic 0, we set the latch output to the logic 1 state. Okay. Similarly, the S terminal is at the set or a preset input. The latch is set at Q is equal to logic 1, and the Q complement is equal to logic 0. So choosing S is equal to logic 0 and R is equal to logic 1 enters a logic 0 into the memory. Okay. So this is actually S, R, and the Q and a Q and plus 1. So this actually the table. So the SR latch to table. So main consideration is that the QN is the current state of the output and at the instant of applying the input combination, and Qn plus 1. Okay, the Qn plus 1 which we are seeing here, this Qn plus 1 is the next state of the output that takes after applying a given combination to the input. So the input S is equal to logic 0, and uh, the input S is equal to logic 0 and R is equal to logic 0, that lead to an unknown state, that is Qn plus 1, could be either logic 1 or logic 0. And with this combination of inputs, the output does not change. That is, the next state of the output is logic 0 if it was logic 0, and logic 1 if it was logic 1. So in this cases, the latch remembers its previous state. Now that is why this is actually the latch SR latch that we call it. Okay, because it remembers the previous state. Similarly, with S is equal to logic 0 and R is equal to logic 1, the output goes to logic 0, regardless of whether it was in logic 0 or logic 1. So this is for the combination for S is equal to logic 0 or R is equal to logic 1. So the output goes to logic 0, whether it was logic 0 or logic 1. Similarly, with S is equal to logic 1 and R is equal to logic 0, the output goes to logic 1, regardless of whether it was logic 0 or logic 1. Now, another thing is that the combination S is equal to logic 1 and R is equal to logic 1 is not allowed, because it produces a state of, you can say, a state of interminacy that must be avoided. So that is why the combination S is equal to logic 1 and R is equal to logic 1 is not allowed. So this actually this set and this set input cannot be logic 1 simultaneously. So the S and R cannot be logic 1 in simultaneously. So whatever we have discussed, so that is actually summarized in this truth table. So as you can see here. Now this is actually logic symbol for set and reset, that is SR latch. Okay, so we have, this is the logic symbol S and this is R, and we have output Q and Q complement. Okay, so this is the logic symbol for the set and reset latch. Now, whatever we have discussed so far for the SR latches, SR latch, that is actually we have obtained through non NAND gate. Okay, so the SR latch is obtained by NAND gate. But let's say if you want to achieve by NOR gate, then how it can be? Okay, so the same thing. just like here, if we can see here, so we have a NOT gate, and the NOT gate output, one NOT gate output is given to the input of another NAND gate, and similarly the output of another NOT gate is given to the input of another NAND gate, and the output of one NAND gate is given to the input of another NAND gate, and the output of again another NAND gate is given to input of another NAND gate. So Q and Q1 is obtained. Similarly, the only difference is that this NAND gate is replaced by NOR gate. So that's set and reset latch with NOR gate can be also determined and can be shown accordingly. So this is actually this our SR latch that is achieved by NOR gate. Okay. The only difference, all things are same. Only the difference, the NOR gate is a NAND gate is replaced by the NOR gate here. So this is the input S and R, that is set and reset, and then S is given to this inverter, that's NOT gate. Then output of this inverter is given to this input of this NAND gate, sorry, NOR gate, because here we are using NOR gate actually. And similarly, the another input which is R, that is given to the another inverter, and output of this inverter is given to this NOR gate, and the output of this all the NOR gate which we have this here, the output is Q, and here the output is Q complement. So, okay, so this output Q which we have at this NOR gate is given to the input of another NOR gate. Okay, similarly the output which we have getting here Q complement, so that we are actually giving to the input of another NOR gate. Okay, so this way the SR latch is active through NOR gate. Okay, so the all the concept and combinations are same, only the difference is that the NAND gate is replaced by the NOR gate here. Okay, so the clocked SR flip-flop. So this is actually how this is actually the improvement of the basic latch. So whatever the latch we have studied so far, so this clocked flip-flop is an improvisation from the basic latch. So it is improvement from the basic latch. Now, in order to implement the sequential system, we need to be able to set or reset the output of the memory element in synchronism with the clock pulses. Okay, so that is very important, because in sequential systems we have a memory element, so which we don't have in the combinational circuit. So in the sequential system, as we need to set and reset the output of the memory element in synchronism with the clock pulses, so that is important. Now in the case of clocked SR flip-flop, a clock signal similar to that shown in figure that we have shown, because in figure 1, if you remember in the morning, I have shown to you, so this is actually the clock's pulse. Okay, this is a clock pulse of train which has period t. Okay, this has period t. So here to here is one period t, again here to here another period t. It's like this is the time period of this clock pulse. Okay, and this is the width of this clock pulse, and this width is very less than the time period t. Okay, this tp is very less than the period t. Okay, the time period. So if we can use this clock pulse here in this figure, so this clock pulse that we have seen here, it can be used to set and reset the output of the appropriate moments. Okay, now with the clocked SR flip-flop, the output changes the state during the brief period of time that clock is actually logic high. So if you can see here, there are four NAND gate here, and they're actually N1, N2, N3, N4. Okay. Now this two inputs that is that we already used. That so here also the same. This is S and R, that is set and reset input, and another is added here, the clock pulse. Okay, the clock pulse is added. Train of clock pulse is added here. Okay, to the input of both the NAND gate, that is to N3 and 4. Now this output is whatever we have from the NAND gate N3 is given to the input of this another NAND gate, that is N1. Okay, now again the another the NAND gate which we have, that is N4, the output of this N4 is output of this N4 NAND gate is given to the input of this another NAND gate, that is N2. Now the cross linking of this NAND, the output of the NAND gate is done. That means the output of this NAND gate N1 is given to the input of this NAND gate N2, and the output of this NAND gate N2 is given to the input of another NAND gate N1. Okay, so now this input which you are giving to the this to NAND N1 and N2, this is designated as A1 and A2. Okay, and this is we are getting output Q and Q complement. Now this is actually the thing, and this is control gates and the latch which you are seeing here, and this is clocked SR flip flop. The figure. Okay, so in the clocked SR flip flop, this is the way how we can design the clocked SR flip flop. Okay, so the only difference is that we have here four NAND gates here, and we are incorporating one clock pulse. The clock pulse which I have shown, that the clock period of T and the pulse width of TP, where the pulse width TP is very less than the time period T. So that clock pulse we generally use, and finally we get use this clock SR flip flop we can able to design. Now, if you can see its description or its working, so if you can see here, the gates N1 N2 actually make a latch. So this gates N1 N2, this actually N1 and N2 that makes a latch, and N3 N3 N4 are the steering gates to set the state of the flip flop when the clock is at logic high. Okay, now, when the CK means the clock pulse. Okay, when the clock pulse actually zero, that means no clock pulse. Then the output N3 and N4 are logic one. So when the clock pulse, that is when there is no clock pulse here. So the outputs of N3 and N4, that means the output of N3 and N4 are at a logic one. No matter what are the value of set and resets are done. Okay. Now, under this condition, the circuit actually behaves like one in figure 2. Okay, the one in figure 2 in latch. So this is figure 2, if you can see. So this is the figure 2. So it will be operate like this. So 1 bit memory that we can see here, it will operate like this as shown in figure 2. Now, um, um, uh, if the clocked SR flip-flop does not change state within the bit time interval, then it is shown in this figure 1 that we know already. Now, if the CK, that is the clock pulse, is logic 1, that is clock pulse is logic 1, then the outputs of N3 and N4 depend on the values of S and R input. So the outputs of this N3 and N4 that we are seeing here, the outputs of N3 and N4 depends on the values of S and R input. So what is the value of set and reset input? The output of N3 and N4 depends on. Okay. Now, if now this is for the when the clock pulse is 1, and the output of N3 and N4 NAND gate depends on the value of S and R inputs. Now, let's say if the set and reset input, that S and R is equal to logic 0, then Qn plus 1 is equal to Qn. Okay, if the S and R is equal to logic 0, then our Qn plus 1 is equal to Qn. Now, if S is equal to logic 0 and R is equal to logic 1, then Qn plus 1 is equal to logic 0. Okay, and if S is equal to logic 1 and R is equal to logic 0, the Qn plus 1 is equal to logic 1. So this is one combination. Now let's say another condition we have to apply. Let's say both S and R, that is S set and reset input is logic 1, then the outputs of N3 and N4 are logic 0. Okay, the outputs of N3 and N4 are at logic 0. Okay, if the S and R is logic 1, if S and R is equal to logic 1, then output of this N3 and N4 are at logic 0. Now then the N1 and N2, outputs must be at logic 1. This N1 and N2 outputs must be at logic 1. This N1 and N2 NAND gate, the output must be at logic 1. Now, this condition is inconsistent that we have defined for Q and Q complement. That is the output for the Q and Q complement that we have seen here. So the output of transistor each gate N1 and N2 cut off, resulting in each output being logic 1. Now at the end of the pulse, the inputs at B1 and B2 rise from logic 0 to logic 1. Okay, the input at B1 and B2 is rise from logic 0 to logic 1. And depending upon actually what or which input increases faster and upon the circuit parameter asymmetric, either the stable state Q is equal to logic 1 or Q is equal to logic 0 will result. Now, since the final result is undefined, we should avoid the condition S is equal to R is equal to logic 1. That I have already discussed here. So, S and R logic is not allowed because this produces a state of inter, uh, you can say, indeterminacy that must be avoided. And the set and reset input in SRLAS can be ignored, and that cannot be logic 1 simultaneously. Okay, so this has to be considered. So as you can see here, so the gates N1 and N2 make the latch, and N3 and N4 are steering gates to state the value of flip-flop when the clock is at logic high. Now when the clock pulse, that is logic 0, there is no clock pulse, the output N3 N4 at logic 1. So no matter whatever the values of set and reset are. Now, under this condition, the circuits that I already told in the first class today in the morning, so that is already in that is behave like a latch. Okay, the simple NOT gate, two NOT gates, where there is a cross the linking of the outputs, so that will behave like that one. Now, then the clocked SR flip-flop that does not change state when the bit time interval will be as per the figure that we have already discussed. So that means that the clock SR flip-flop does not change state within the bit time. That bit time interval, how the where our clock pulse has a period t and the pulse width is tp. So the pulse width is less than the pulse interval, that period time interval. So that is actually needs to be considered. Now, when the clock pulse, that is logic 1, then the outputs of this N3 and N4, the N3 and N4 is equal, depend on the values of S and R inputs. Now, if S and R is equal to logic 0, then Qn plus 1 is equal to Qn. If S is equal to logic 0 and R is equal to logic 1, then Qn plus 1 is equal to logic 0. If S is equal to logic 1 and R is equal to logic 0, then Qn plus 1 will also logic 1. Similarly, another condition where S and R, that is the set and R, set and reset input, that is S and R is equal to logic 1, the outputs of N3 and N4 are logic 0. Then in that cases, our N1 and the N1 and N2, this N1 and N2 NAND gate which we are seeing here, that output must be at logic 1. Now this condition actually inconsistent with our definition of output, that we have Q and Q complement. So the output transistor of each gate N1 and N2 cut off, resulting in each output being logic 1. Now at the end of the pulse, the inputs at B1 and B2 rise from logic 0 to logic 1. Now, depending upon which input increases faster and upon the circuit parameter asymmetries, either the stable state Q is equal to logic 1 or Q is equal to logic 0 will result. So now, since the final result actually we can't able to determine, that is the final is undefined. So we should avoid the condition S is equal to R is equal to logic 1. So we should always avoid the condition the set and reset input is equal to logic 1. Now this is actually how the commercial CMOS SL latches looks like. Okay, So this is actually our commercial CMOS logic here. So if you can see here, this is actually the block diagram of CMOS SR latches. Okay, CMOS set indices latches. Okay, this is the block diagram of that we generally call Fairchild CD 4043 BC. So this is actually the abbreviation. Fairchild actually the one company in USA that made this latches. Okay, this Fairchild is a company name which made these latches. So this quad cross couple three-state CMOS NOR latches, and its truth table is this one. Okay, so this is our the PMOS and NMOS. If you can see here, we have here, and this two NAND gate here, and these outputs are the cross linking with each other. It's a NOT gate, and this is our NAND and NOR gate. So like this actually the block diagram of CMOS SR latches. Okay. So if in the question it is asks commercial CMOS SR latches to draw, and then you have to draw like this. And what is the truth table of this CMOS SR latches? So this is set input E and Q output. But what is OC here? Open circuit. Okay. What OC? Open circuit. NC means no change here. Okay. X is equal to that is don't care, and this del is equal to dominated by S is equal to one input. Now this figure 8 that we are seeing here, this is actually block diagram of Fairchild CD of 4044 BC, that is quad cross coupled three-state CMOS NAND latches, and this table 4 shows the truth table. So as you can see here, so we have the NAND gate with cross linking of the outputs with each other, NOT gate, and this NAND, NOR gate, and the PMOS and CMOS which we have. Okay. And another thing is that this is the supply voltage and this is the output Q, and we get the truth table like this. Okay. So we can see here, the two dial operator which you have seen here, that is dominated by R is equal to 0 input. Okay. Now according to Fairchild data sheet, generally each latch has a separate Q output and individual set and reset inputs. Okay. There is a common three-state enable input for all four latches. Now a logic one on the enable input. So this is our actually enable input that we have, connects the latch state to the Q output. Now a logic 0 on the enable input disconnects the latch state from the Q outputs, resulting in an open circuit condition on the Q output. Now the three-state feature allows the common busing of the outputs actually. Okay, so this is actually very important. So you need to know what actually the commercially you can say the CMOS NAND latches. Okay, this is CMOS NOR latches. So how this is? So and what is its truth table? Okay, so this is actually our the block diagram of Fairchild. That is CD4043 BC. So this is actually the nomenclature we are using. So this is for CMOS SR latches. Okay, CMOS NOR latches, and it's the figure along with this truth table. Similarly, this is for three-state CMOS NAND latches. Okay, with this truth table. So about CMOS SL latches and flip-flops, we can finally conclude that so the present state of combinational circuit that doesn't depend on the previous state of the inputs. Okay, so it has no memory, and the output depends on the current combination of the inputs only. So this is actually all about the combination circuit, because there is no memory elements we are present in the combination circuit. So present state of the combination circuit that doesn't depend, never depend upon the previous value of the inputs. So because it has no memory. Okay, and the outputs depends on the current combination of the inputs. So what are the output we have in the combination circuit? So that only depends upon what is the combination input at that time. Okay, so that actually come in the combinational circuit. But in sequential circuit, as it has a memory, So the output depends on the combination of the present inputs and the logic state of the inputs at previous time. So that is very important. So that is actually the difference between the sequential circuit and the combinational circuit. So as in the memory, so the sequential circuit has a memory. So the output depends on the combination of the present inputs. Okay. Now the clock is an external and usually periodic logic signal. So that is generally used to synchronize the signals in complex circuits. Now, a latch can store one bit of information by remaining intermittently in acquired states. Now, the input to an SR latches, that S is called set and R is called reset. The outputs are actually Q and Q complement, okay, which we have so far discussed in today's class. Now, when the input actually R and S are logic 0, the output remembered the previous states. Now making S is equal to logic 1, the set operation, that changes the output to Q is equal to logic 1 and Q complement is equal to logic 0. Okay. Now making the reset, that is logic R is equal to logic 1, the reset operation, that changes to the outputs Q is equal to logic 0 and Q complement is equal to logic 1. Now we need to avoid always when the set and reset logic is equal to 1. So always we need to avoid this S and the reset of combination to be logic 1. So that is very, very important. Now a clock flip-flop accepts the input state during the brief period of time that the clock is logic high. Okay. So this is actually so far we have studied for this CMOS latches and flip-flops. So today we have discussed a brief details about CMOS SR latches and the flip-flops. Then a brief introduction about flip-flop, how it is operates. Then the difference between combinational and sequential circuits. So what is the difference and how the output depends upon the depending upon the type of circuit which we have. So whether it is combinational circuit and sequential circuit, that depends on what type of circuits we are using. In combinational circuit there is no memory element, but in sequential circuit we do have memory, so the output depends upon like this. So along with this, when we have the sequential circuit, we have to incorporate the clock pulses. So the clock pulses actually look like this. So and the condition is that the we have the pulse width and the pulse time period. So we have to determine accordingly. Then we discussed about storing, how the storing of one bit of information is possible. Okay, so how the one bit of information possible. So this is the simple latch that we have discussed. Now then we discussed about SR latch. So in this case the SR latch is developed with two NAND gate. Okay, with two NAND gate we developed SR latch, and we discussed about its working and its truth table. Similarly, the to SR latch logic symbol, and after that, how the SR latch can be achieved through NOR gate. So that we discussed about SR latch through NAND gate. Now this is through NOR gate. Then we discussed about clocked SR flip flop, and in the clocked SR flip flop, we have four NAND gate, and we are incorporating clock signal, and, and after that we getting the outputs accordingly the type of logic we are using. Okay, and this is our commercially CMOS latches. So this is actually CMOS NOR latches. It's figure along with the truth table, and similarly this is actually CMOS NAND latches with figure with the truth table. Okay. Okay, then so this is for today's class. So we'll meet tomorrow. Okay, so tomorrow we'll do one thing. Tomorrow we'll take a combined class. So tomorrow we'll take a combined class between afternoon 1:30 to 3 p.m. Okay, so tomorrow 1:30 to 3 p.m. we can take a combined class. Okay, so that we'll study some more contents as per the contents which we have. So we'll continue with our session tomorrow. Okay. So with this, so let's close our session for today's class. So we'll meet tomorrow then. Okay. And for the those students, those who have not yet shown me the lab, only the lab students. So they should show me the results of today's experiment, and then we can wind up accordingly. Okay. So with this, so let's close this session. So we'll meet tomorrow then. Okay. Thank you, everyone.